changes exponentially?
It's actually kind of a hard question.
It is, isn't it? It really is.
There's something in physics, but I can't remember it at the moment. So,
Let's talk about the one thing that we all like. We all can agree that we like. There's a single person here that
well, I mean, it is cell growth.
we can all agree that we like one thing.
Money.
We all like money, okay? And sometimes when you talk about money, you say, okay, I'm going to put my money in an investment, and hopefully that investment does what over time? Increases. But then each time that they go ahead and they accrue some interest to that, then you've got a new balance, and hope that balance is what? Higher, and then after that, higher. But here's an example, okay? I'm not sure if this is the best example to use in the world, but it's an idea of exponential growth. Let's just pretend maybe you were gambling one day, okay? And you start with a $1 bet. Let's say you win your $1 bet. What are you up to? $2, okay. Okay, so say you take that $2 bet and bet all $2 now.
Oh, now you get 4.
Now you're up to 4. And then 4, if you bet that win, you're up to what? 8. And then 8 turns into 16 and so on. Okay, you want to know how much money $1 could be if you got 21 bets in a row, right?
I could probably figure it out.
Yeah, I already know
Take
it.
2 to the 21st power. See what that is.
Just let me use my mind calculator.
4, 8, 16, 32, 64, 128.
That would
56,
be 2,097,152.
So a little over $2 million, right? If I could bet my previous amount each time and win 21 times in a row, by the 21st hand of gambling, you would have over $2 million.
In the words of my 3rd grade teacher, Vanessa Arhart, gambling is fun, especially when it's not your money.
This is true.
Oh, did you
This
hear
is
about
true.
the guy that won Jeopardy 32 times in a row?
Yeah.
He worked in Vegas as a bet placer.
Yep.
That's really cool.
It's pretty impressive how they do that. A lot of very number-minded, good number sense people that do stuff like that. I think I could have fun doing that. I should go practice up at the one up there, see how well I do there.
The aisle.
Mm-hmm.
I mean, all that, the people that go up there are all old people.
They
are.
I gotta be honest with you, I've probably only been in that place like 3 times, and 2 of them were to eat.
I used to go there all the time with my grandma did. And funny thing is that my grandma on my dad's side met my great grandparents on my mom's side.
Yeah.
My dad's
That's cool.
my dad's side met my mom's side, and it was so
Yeah.
weird. Like,
I don't know how people go up there and just, I mean, money is, some people bet a lot of money or gamble with a lot of money. I lose like $10 and I'm like freaking out. I was like, okay, we're out of here. So,
Our
kind of
parents
crazy.
tell me to go in with a set amount and then go over.
That's true. You could do that. You could do that. It's hard to do though,
Or
because
just go in with something.
eventually you
that's
think
not
you
your
should
money.
win. But anyway, that idea is that if you could win 21 hands in a row and keep doubling your bet, $1 turned into $2 million pretty quickly, didn't it?
Of course.
Okay, so that's kind of what we're talking about today. We're going to talk about things that grow exponentially, things that might start out slow and then start changing. The rate of change becomes very rapid. It might grow rapidly. It might decrease rapidly. You guys have probably had science classes where it said a culture starts out with like a set of bacteria and doubles in a certain amount of time. How many bacteria are in there after so many minutes, that type of stuff. You've done stuff like that, so it's kind of related to that. So today what we need to answer is the following. We need to know what an exponential function is and how it's applied to real life situations. And I think the thing that you're finding out about most of these problems that we're looking at, not so much drill and practice, can you find me an equation, or can you write a function? It's taking those functions and then actually doing what with them? Yeah, a lot of this is going to be application here. So guys, our job today, understand general exponential form. We're going to determine if a function shows growth or decay, and then we're going to model real life problems with exponential functions. Now I want you to realize something. Just because last section was about linear functions doesn't mean we just forget about them in this section, because there's some things that are going to come up that we've looked at already, so don't lose sight of what we've already done. All right, exponential functions. How about a volunteer to read that definition for me?
Oh, I guess I will.
Thanks,
That was a long
Kylie.
pause. P is an exponential function t with base a if p equals p initial probably.
Yep, piece of O, if you want to
And
call
then
it. Yep.
a to the t power, where p of o is the initial quantity, where t equals o, and this is 0.
Yep.
Okay. And a is the factor by which p changes when t increases by 1.
Absolutely, very good. So what they're really saying is P is some value. Piece of O is how much you, piece of O is an initial value. So it's basically it's really saying what are you starting with, okay? That's what piece of O says. A is like a rate of change. If I say something doubles over time, what's the rate of change? What value would you use for rate of change if I said something doubles over time? 2, okay? If I said the half-life of something over a certain amount of time, what would the A value be? 1/2. 1/2, okay? So A is going to be some value. I don't know if it's going to be more than 1 or less than 1, but kind of want you to put this into perspective. If I have an A value of more than 1, is that going to indicate growth or decay? If I take something to start with times a value bigger than 1, is that going to grow the value or decay the value?
Growth.
So anything above 1 would indicate growth, which means anything between 0 and 1 would mean like a fraction, 1/2.
Decay.
Yep, so keep that in mind, and we'll talk about that a little bit in some examples. T is typically some kind of a time measurement. And then that p-value that you're talking about is the amount you end with, okay? So the p would be the amount, I'm just going to say the end amount in all of this, okay? So a lot of wordiness in there. If you can just remember those things right there in terms of exponential form. And exponential form, again, kids, this formula is going to come up a lot. So you might want to highlight that or box that in. This is going to show up a lot, okay? All right, you're going to hear things like concavity today. We talked about increasing, decreasing for linear functions in the last section. In this section, you're going to hear about, is a graph concave up or is a graph concave down? What's it say about concave up, kids?
Graph that bends upward as you move from left to right.
So as I move from left to right, that would be an example of concave up. Okay, it's goofy. Another example of concave up, my graph is decreasing, but everything's starting to bend in what direction here? It was really negative, so we're kind of starting to bend it towards the, that makes sense to you? These are examples of graphs that are concave up, so I'll put arrows in there like so. Okay. What's an example of a graph that's concave down then?
Graphs that bend downward as you move left to right.
Something like this, or, you know, if you had an increasing line and you bent it down, let me just draw like a straight line in here. If I had like a straight line right here, did I bend that part up? If I had a straight line right here, kids, did I bend these parts up to get that?
Yes.
Does that make sense? So if I had straight lines here with these, did I bend those down to get those curves, kids?
Yeah.
Okay, so you understand the difference between concave up and concave down? Think of an umbrella, shape of an umbrella. The umbrella top, is that concave up or concave down? Down, right? Okay, if I was to pour water on that umbrella, would it run off or would it stay inside of it? It would run off. Stuff that runs off is going to be considered concave down. Think of a bowl. Is that bowl going to hold water or let it run off? It's going to hold water, so if it holds water, it would be concave up. So maybe think of it that way. Concave up is kind of what we call a bowl simulation. If it holds water. Concave down, what's a good name for that? It's an umbrella. Okay. All right, how about doubling time, kids? What's it say there?
Time required for a population double.
Okay, we're going to talk about examples like that. What do you think halftime is? It's not between second and third quarter of a football game.
Time required for a population cut.
Oh, come on, that was good, guys.
To be,
Ha ha ha.
a little bit cut off.
I know. Is the time required for a population to be cut in? Half. Right there, on the second page there. Yeah, I got kind of cut in half, didn't it? Oh.
It did not get cut in half. That is not a fraction.
There's two parts, right?
There's three parts. There's two
It's
parts,
been
but
cut
most of it is
in
on the
twain.
top.
3 lines.
It's been cut in 2 parts.
Okay, you win. I'll let you win. You win.
I don't know.
You win. Okay, hey, do we know what a horizontal asymptote is?
Yeah, we've talked about.
We've talked about them. Give me an example, or maybe, let me read this real quickly, and then maybe you kind of talk to me about how to sketch this. It says, if the graph of a line approaches a horizontal line y equals capital L, as x approaches infinity or as x approaches negative infinity, then the line y equal L is considered a horizontal asymptote. So how would I sketch a horizontal asymptote, or a graph that has a horizontal asymptote, kids?
Dotted line.
Okay, I'll put the dotted line maybe right here. And let's call that line y equals capital L. And then we're looking for some graph that approaches it, but will it ever cross it, kids? So is this possible right here? Is this a possibility right here? Kind of like that, never crosses that? That would be an example, right? So likewise, a vertical asymptote then. A vertical asymptote, if the graph of y equals f of x approaches the vertical line, x equal k as x approaches k from either the left side or the right side, then we say x equal k is what type of an asymptote? Yeah, and we've talked about this, kids. So there's really, I'll sketch, here's an xy axis. My dotted line going to be vertical or horizontal, kids? Yeah, so we would have probably a vertical line right here. And this is not y equals some number, this is x equals some number k. Don't know what it is, but maybe we have a graph that does this for it. Maybe it, I don't know. Maybe it comes through here and then down. It comes through here and then. By the way, does that have a horizontal asymptote the way I've kind of drawn it?
Yeah.
Okay. What would the horizontal asymptote to that graph be the way I've drawn it?
The
The x-axis, okay? So I think terms-wise, you'll be in pretty good shape today. As long as you've got an illustration or some shortcuts to the definitions, I think they should make a lot of sense. Okay. Anybody need more time with those illustrations? Feeling okay about them? All right, let's get into some examples here. I like this first example right here, determining if data is exponential or not. Guys, data that's exponential is kind of like what we talked about with that money situation. 1 turns into what? We doubled it to what? 2. Then 2 doubled to what? 4. And then 4 we took times 2 to get to 8. Each time we were doubling the previous value. We're multiplying the previous value by 2 to get to the next value. And that's what it means to have a table of exponentials. You take one value and multiply by the same to get the next value. So if I look at these 3 tables, we'll call this table 1. Let's highlight them in different colors. Maybe this is a table right here. There's one of them. See any patterns of there? All the x values in each table go up by the same amount each time. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. Look at your output values right here. You notice a pattern right here?
Those are exponential.
Why are you saying that, Kylie?
They don't go up by the same amount every time.
Okay, is there a pattern to go from 9 to 27 to 81?
It's multiplied by 3.
So you're taking one value here. So you're saying to go from 9 to 27, you would multiply by 3. How about here? Times by, is this true here? Times by what? Same here? Now, I would have to say you're right, and I could also look at it this way. Maybe look at 27 and work backwards. 27 divided by 9 would equal what value? What would 81 divided by 27 equal? What would, and so on, okay? What's true about all those multiplication values, or what are true about all those multiples right there? Well, we're always multiplying by 3. So down here, we're going to say, is this going to be a situation that's exponential or not?
Yes.
Okay, it's going to be exponential. And are my values getting bigger or smaller, kids? So this is actually going to be an example of exponential growth right here. Okay, how about my next table right here? In the second table.
Looks pretty linear to me.
Why are you saying linear?
Those are not multiplied to each other.
Yeah, I can't multiply, but is there a pattern going from 12 to 8 to 4 to 0 to negative 4? Yeah, it's decreasing by 4 each time. So when I say, well, we're going from here to here, we minus 4 to get there. We minus 4 to get there. Anytime you're adding or subtracting the same amount, then that becomes what type of a function again? Yeah, this is actually linear. Is this going to be an example of linear growth or linear decay, kids?
Decay.
You bet, linear decay. Alright, so I'm curious to see what you guys think. Is there a pattern that sticks out in the next one?
Maybe if I.
It's divided by 2. Oh, well.
Close.
Kind of divided by 2.
Kind of. I can, okay. Is there one that I can rule out? About how much does this go down by the first time? Just estimate, 530. Does it go down 530 again to get to the next value? So am I going up or down by the same value at all?
No.
So we know this table is not what?
Exponential.
It can't, well, we don't know that yet. We know it's
Or
not
linear,
linear
sorry,
because it's
sorry.
not adding or subtracting the same amount each time. Right? Here's what I would challenge you to check here, kids. Like I talked about kind of here, we said, well, we see this easily. It's easy to see that we're multiplied by 3 over here. So what I suggest is, by the way, what if we work backwards and said, what's 27 divided by 9? What did you get? 3, right? And then did 81 divided by 27. What did you get? 3 again, right? Let's apply that logic over here. Let's check and see what 413.68 divided by 951.46 is approximately. Let's go 2 places if it's not a nice decimal.
Well, it's not a nice decimal.
What is it to the nearest hundred?
0.43.
So to go from here to here, we can multiply by 0.43. Let's see if that holds true throughout the rest of the table. So now, I want you to take this 179.86 and divide it by 413.68. What do you get? Same, point what?
0.43.
Check the rest for me. See what this divided by this is.
I feel a lot of pressure. It's the same for the next one.
Okay. One more, Kylie.
Yeah, I'm not surprised it's the same for the next one.
Okay, so do you guys agree that to go from this value here to this one, to this one, to this one, we would take this value and multiply it by 0.43 to get the next one each time? So if I'm multiplying by the same amount, does that indicate some kind of exponential change? Absolutely, okay? This time though, instead of exponential growth, what's happening here? Yep, this would be an example of exponential decay because we're multiplying by 0.43, so I'll put this little multiply in front of them. You might want to do the same. Yeah, anytime you multiply by the same amount to get from one value to the next, and that pattern repeats itself throughout the table, that indicates that that is some kind of an exponential change. And you said exponential decay, because my values are decreasing. Very good. Alright, anybody need more time with the table there? Got what you need so far? So do we kind of get this idea of exponential growth and decay right now? You're either multiplying or, I should say, growing or decaying by the same multiple from one value to the next. Okay? Values more than 1. If I multiply by values more than 1, am I growing or decaying?
What's growing?
If I multiply by values bigger than 1, we're growing.
Oh,
If I multiply by values between 0 and 1, what's happening to my initial value? Absolutely. Okay. All right, I like this example 2. I think if you can understand example 2, you're going to do really good things here. Okay, how about a volunteer to read that example 2 where it says find populations from exponential models? I'll read it. It says the population of the United States is in 2010, or when time t equals 0 was approximately 308.7 million people. And was growing at a rate of what, kids? 7.26% per year. Okay. By the way, anybody know what the population of the U.S. is right now?
Is it in?
I know it's in the 300 millions, isn't it?
Oh, okay. That's what I was about to say, but I didn't want to sound dumb.
Think. Anybody have a phone? Can you Google that up for me, Miss KP? While we're doing this, okay. It says use this model to predict the population in the USA today. Okay. Today being what year then?
That would be 2030. 2019.
Okay, and then we're going to use that same model to predict the population in 2025 using this model. Okay, guys, I want to go ahead and allude to something right here. Population growth. Got it, buddy?
327.2 million.
Let's see how close this problem really is. 327 point.
2 million.
Okay, we'll see if we're close on this. Okay, remember I gave you that idea that the population P is equal to P sub O times A to the T, okay? Now up here, I want you to come up here and write this down here. Sometimes, guys, A can equal 1 plus or minus R. If I do 1 plus R, that's representative of growth. If I do 1 minus R, that's representative of decay. So what I'm getting at here, kids, is this. If I increase something by 7.26%, don't I have 107% of the original value? Or isn't everything 107%? Okay. So in this problem right here, is our population growing or is it decaying? Okay. So I'm going to use this idea that A is actually going to equal 100% that we initially start with plus the percentage rate we would add to it. So, since this is growth, an alternative formula would be the following. P equals P sub O times 1 plus our percentage rate as a decimal to the T power, okay? So here we go. We want the population in now, right? Well, the population now is going to equal the population when we started. What was the population when we started? 308.7. Okay, my A value, or in this case, the 1 plus the percent increase that we have. Oh, I don't know. How are you going to write 7.26% as a decimal?
Oh, 0.0726.
So add 1 to that. So if you guys agree, my A value is 1.0726. Okay, if I want the population now is what year, kids? 2019 time t equals 0 was relative to what year up here when we started? So what t value should I put in here to find the population right now in 2019? Okay, who has a calculator? Okay, you want to run that mess for me? 308.7 times 1.0726 to the 9th power. What'd you say again, KP? According to Google?
327.2. That was as of 2008. 726. I don't know if I did this right. I got 576.4.
Well, let's see. It's very possible. Maybe
That'd be
this
really
is,
weird though.
I don't know. 1 point.
Dude, I got 500.
You got 580?
0726 to what power? And then times that by 308.7.
That might be where my mistake went.
I'm getting 580.
Oh, okay.
Okay. According to this model right here, is this model correct or incorrect right now?
Incorrect.
Okay, bad. According to this model, the population should be what? 580 million, right? And is it?
Not even close.
Not even close. Now, if we use this model right here, they want the population in 2025. If this model was true, kids, do this for me. Google up the United States and find out ask it at what rate is population growing in the United States right now. What would I plug in for my t-value here, kids? How much?
15.
Why 15?
15 years after 2010.
Yeah, 15 years from 2010 would make it 2025. So this is going to get to be a pretty big number, isn't it?
Yeah, it's 883 million.
883 million. That's a lot.
Did you write this problem?
No, I just took it from a problem that was already written.
The problem that was already written is disappointing me.
I agree. What's that mean then about the population? If this was true in 2010, if this was true in 2010, what's happened to the rate at which the population is growing? Increase or decrease?
Decrease.
It's a decrease if that was true. Does it say what the percent change is or how?
Yeah, it says the U.S. population growth is running between 0.7% and 0.9% per year.
Okay.
Oh, that's
I
way
can search
smaller.
up the population in 2010.
What was the population in 2010?
$309.3 million.
So pretty close, right?
Yeah.
Crazy. Ask Google if they think the United States population will ever reach 1 billion. Oops.
That'd be pretty wild. I don't know if we have room for all of us.
I mean, that's 3 times. What are we at? 320. That'd be about 3 times the population. Okay. I'm just curious. What's the population now? You've got me thinking, guys. I want to do this.
You said 327 million?
327 million is the population now, and it's growing at what?
What?
What's the population rate change right now?
0.7% to 0.9% per year.
So let's just assume 0.8. Is that all right? So if this was the model right here, right now, 2025, it was 2019. How many years is 2025 from us right now? 6? So if I took 1.008 to the 6th, and then times that by 327, this tells me about 343 million will be our population in
We are on
2025.
track for a population of 1.182 billion people in the year 21,000.
2100?
That's an unreasonable long time to think ahead.
Well, I won't be around to see that. I can tell you that much right now. Were you guys?
2100.
What were you guys born? 2005?
2003.
2003?
Yeah.
You might make it to 97 years old.
Oh, that's how soon that is?
Yeah.
Something's gotta happen for a lot of people to live in the US in that time to triple our current
I agree.
population.
I agree.
90 years. And 80 years.
80 years. Yeah. It's crazy, huh?
We're on track for that?
Yeah. We're on track for 1 billion by 2100, you said?
Yeah.
Crazy.
Ruh-roh.
Well, I don't have to worry about it. Now my
That might be a
kids
lot.
might have to worry about it. Okay, let's do this. I want to get back to example 3 here.
Guys, this is a pretty interesting problem right here. Okay. They're telling you guys to write an exponential function under some conditions. And in this condition, they say if f of 3 is equal to what, kids?
18.
And f of 7 is equal to 155, we need to write a function to model that. Now again, what type of function?
Exponential.
Okay, I want to talk about this here real quickly. I want to make sure you understand this. We always say p is equal to p sub o times a to the t power. Now, when you do these, kids, you're going to set up two functions, and I want you to be very careful on this. I would always take the one that has the higher value, higher independent value here. So in this case, comparing f of 3 and f of 7, which value is higher? The 3 or the 7? Take that higher independent value first, okay? So here's how we're going to set this up. This is simply saying the following, kids. You're saying that at time 7, your value p in the end is what value? Okay, so the way we set this up is as follows. We're going to plug in as much as we can. We're going to say 155 is my end result here for this one. So I'm just going to put that in for p. That, my friends, is going to equal p sub o times a to the, how much time elapsed to get to 155, kids?
7.
Put a 7 up there. Okay? Then, right below that, put a line. And we're going to do the same thing for f of 3. Well, what did f of 3 equal, kids?
18.
So what we do here, kids, is this. We say 18, then would equal p sub o times a to the what?
Oh, we subtract those.
Well, we don't end up subtracting. Here's kind of what we end up doing. I'm going to show you this right here. Do you guys agree that 12 is equal to 6 times 2?
Yeah.
Do you also agree then that, let's do this, let me agree that 4 is equal to 2 times 2? Guys, what do you get over here? What's the 12 divided by 4 equal?
3.
What's this mess over here equal? What do the 2's do to each other?
Cancel.
And it's really 6 over 2, which is equal to what?
3.
So when I divided these two, and I came over here and took this mess and divided it out, what was true about these two values? They were the what?
Same.
So if 155 is the same as this, and 18 is the same as this mess, wouldn't 155 divided by 18 be the same as this mess over this mess?
Yeah.
So let's go to the nearest tenth. 155 divided by 18, what do you get there?
8.6.
I'm sorry?
8.6.
Okay. Now, why is this important? Well, here's what happens. What do the p sub o's actually end up doing to each other?
Cancel.
They cancel here, okay? And the assumption is p sub o isn't 0, because in order to start with something and get to 155 exponentially, you had to have something other than 0 to start with. Guys, what do you know about a to the 7th and a to the 3rd? When you divide those out. It's a to the 4th power, right? Now, that's going to allow us to solve for what here, kids? Okay, well, what power am I going to have to take this to? I got to take both of these to the 1/4 power. So in your calculator, you're going to want to take 8.6 to the 1/4 power, okay? Put that 1/4 in parentheses for me.
1.7.
I'm sorry?
1.7.
So here we have 1.7 equals a. Now again, our job is to write a function for this. We want to have p equal to some additional value that we'd like to know times a to the t power. We want to be able to write a function p as a function of t here. Well, kids, I have a question. Do we know the a value now?
Yeah.
Okay, so let's do this. I'm going to change colors on this. From here, we know that a is.
1.7.
So let's put that information in. Let's come down here and say, okay, from this I know, or I could say p is equal to, do we know what p sub o is yet?
No.
Not a clue. But do we know what a is now? Okay, now, the only thing we need to do is to figure out that p sub o value to write that function. And here's how we're going to do it. Go back up to the information they gave you. How many points did they really give you?
2.
2. Let's plug one of them in. Maybe when t is 3, p is what value? Okay, what are you going to plug in for p? What are you going to plug in for piece of O? Don't know. Don't care at this point. We'll get there. But this would be 1.7 to what power, kids? Okay, so run that 1.7 to the third for me.
4.91, but 4.
So 4.9 piece of O. How are you going to find piece of O, kids? Divided by 4.9. What is 18 divided by 4.9?
It's about 3.7.
Okay, so we're going to see how close we are. So we've got piece of O to be what value?
3.7.
And we have A to equal.
1.7.
So over here, our function is the following. P equals piece of O, which is what value now?
3.7.
Times 1.7 to the t power. Okay? Let's see how close we were. Somebody take 1.7 to the 7th power for me. Take 1.7 to the 7th. You guys got that number?
Yeah. 41.
Now times that by, I get 41.03. Times that by 3.7, see what that is. I get 151.8. Are we kind of close to that 155 that we were getting at? The only reason we didn't get to exactly 155 is because of some rounding things, okay? But do you understand what we did there? If they say, hey, here's 2 points in this, write me a function, really the two values you need to solve for are piece of O and what else? You need to see what those two values are right there, right? All right. So our function, p equals 3.7 times 1.7 to the t is an approximation for that. Questions on that example at all? Let's see what's next here. Oh, we don't want that. All right, last thing we need to look at is determining if a function has asymptotes. I ought to look at this. Sometimes my formats, I write all of these things up in Google Docs now, and then sometimes the format doesn't transfer over. So let me check something here real quickly.
Has anyone seen The Lion King recently? It's a great movie.
I have. Well, it was in the summer when I
Yeah,
saw
I've
it.
seen Hamlet.
Leo watches it all the time.
I watch it all the time too. Home Alone. I watch Home Alone a lot as well. It's a good movie.
Oh, come on. Gosh darn it. Hang on a second, kids. 18. Okay, that should be 6 over x minus 4. Okay, 6 over x minus 4 plus 3. Just gotta do it this way. 6 over x minus 4. I think the bar's already there for you, isn't it?
Yeah.
Ours says that.
Ours says 6.
Oh, it does?
Yeah.
Awesome.
Our whole thing is in.
Okay, okay. I'm sorry, I wasted your time there. Guys, vertical asymptotes anywhere? Is there any value x cannot equal here?
Oh, 4.
Yeah, x can't equal 4. So a vertical asymptote would occur at x equals what, kids? Okay. Any horizontal asymptotes here? Any question about horizontal asymptotes? Horizontal asymptotes occur as x gets very large. Listen to what I say here. If I make x a really, really large number here, kids, this will be a value, let's pretend it's on the positive side. So this would be like 6 divided by some very large positive number. 6 divided by some very large positive number would be really, really close to what? 0. But then we're going to add what? So we're going to be getting really, really close to really what horizontal asymptote here? 3. Think about it. What if this was really big negative infinity? 6 divided by something really big on the negative side would be really, really close to 0. But think of it this way. Guys, we can get close to 0 by approaching it from positive values or approaching it from negative values, right? Well, guys, if I have like negative 0.001 right here, isn't that going to make that about 2.99? So you're going to have something approaching 3 from the bottom side and then something approaching 3 from the top side. So what do you think the horizontal asymptote is going to be in this? Y equals how much? Okay, let's just check. Let's just jump into decimals and see here. Somebody punch that function in decimals. I'm going to take this down here so I can do that also. 6 over x minus 4 plus 3. Let's check it out. What the heck? Oh, I'm there already. Duh. Okay, what was it? 6 over x minus 4?
Plus 3.
Okay. Plus 3? I gotta kick that out, don't I? Okay, just looking at this, I'll zoom out once, but does it look like right here at maybe 2,4, does it look like right here there might be a vertical asymptote here? I'm just gonna type it in. What did we say the vertical asymptote was gonna be? X equals what?
4.
Guys good with that? What do we say maybe about the horizontal asymptote? What do you think? You think we nailed it? Okay. I get stuck on some of that. Think about the infinity. What happens to this? Well, it gets really, really close to 0. It might be a positive 0.001 or a negative 0.001. Either way, you're never going to get to 3 because this will never, ever equal 0. I would encourage you to graph some stuff. And when you graph it, once you think you know what your vertical and horizontal asymptotes are, punch them in there and see if it matches the graph part right there. I think we've done a pretty good job there, honestly. Okay. Kids, up on the board, your assignment here, page 21, 1 through 32. What numbers do I want you to omit? Now I know I've got some down there for peer work to look at. We'll look at those first things tomorrow. I haven't decided on a due date yet. I'm kind of leaning towards Tuesday of next week, so we'll see what we can do. But how many problems do I have picked up to do together there?